I want to track both angle and position of a device using computer mice. One computer mouse is insufficient. I have a little animation here to show you what a single mouse is able to do. So if I just go ahead and hit play, if I move it up, it'll move up on the display. If I move it to the right, it'll go to the right on the display, and yada yada. And I can translate in both directions at once, no problem. However, there is an issue. If I rotate it, as you can see, I'm moving it up and down, yet the computer thinks it's going left and right. Or if I move it left and right, it thinks it's going up and down. That is not what I want to accomplish. I want to be able to figure out the position and angle of the mouse throughout the entire plane. As you may have noticed, if it's being rotated about a single point, it doesn't move the it doesn't report as moving up or down, left or right. And then just once again for clarity, if this rotates about this middle point, it doesn't move the display, or doesn't move on the display for standard computer mice. Another thing to note is as long as you're moving on an arc of a circle, I'll just go ahead and play the video. As long as you're moving on an arc of a circle, the computer mouse doesn't think it's moving to the left or to the right. It thinks it's moving in a straight line. And as long as it's moving on that arc of a circle, it will continue to think that it's moving in a straight line. And then just once again for clarity, the mouse, it's moving straight along the arc of this circle, and it thinks this is the vertical displacement that it's assuming it's having. And even though this is a curved path, it thinks it's only moved up and down. A single mouse has only 2 degrees of freedom. It can move left and right, and it can move up and down. And those are the only things that it can report. But what I'm wanting is 3 degrees of freedom. I want up and down, left and right, but also rotation. And 2 degrees of freedom of the mouse is not going to be able to deliver that to me. I plan to accomplish this, getting all 3 degrees of freedom, by using 2 mice. And that will allow me to have 3 degrees of freedom and even a redundant degree of freedom. Because there's 2 degrees of freedom per mouse. There are a few things that I want to point out. First, this yellow A is, I'll just go ahead and hit play. Stop it there. This yellow A is the vertical Y distance that the mouse A is reporting. The blue bar here is the vertical distance that the B mouse is reporting. RA is the distance from the center of mouse A to the center of rotation, which in this case is also the center of mass for simplicity. And then RB is just the same thing. It's the distance from the center of mouse B to the center point. And that's the center of rotation, which also happens to be the center of mass. C is the distance between centers of A and B. It is just basically how wide the mouse is. And then the green dot is the center of mass of the 2 things. So here is the animation of the mice as they go through their path, and you'll notice in the top right corner here, the box has rotated. It's been able to track that the mouse combination has rotated. In this case, we don't have any translation because it rotated about the center of mass, so there's no translation there. But it was able to track the angle, and I'm going to be using theta to denote the angle. Things I should also note is that this is a positive rotation. I'm going to denote counterclockwise rotation as positive, which will come up in future calculations, but it doesn't really matter. You can pick whatever convention you want. Another thing to notice is that a is actually a negative value. It's not positive. That would be because instead of moving up in the circle, it went down in the circle. And so yeah, this mouse would be reporting a negative number. If you remember back from high school, or probably even earlier than that, but just general geometry, the circumference of a circle is 2 pi times its radius. So if I go back to the beginning, no, I can do it from here. If I divide this blue length, or in this case it would only be this long. If I divide this blue length by this pink length, then if it becomes about 6.28, or 2 pi, then that's 360 degrees. If I divide this blue length, let's say it went all the way around here, if I divided that by this pink length, then, and it came out to be 3.14, pi, then it would be 180 degrees. And so basically, I can get my theta by dividing the arc length by my radius. That's called a radian, if you're familiar with that. And a radian is just another way to measure angles. There are 6.28 radians in a circle, and there are 360 degrees in a circle. Something that should be noted is that our theta can be calculated by dividing the B arc length by RB, or the A arc length divided by RA. Of course, it will have to be negated because it goes in the negative direction. Because negative times a negative is positive, and this is a positive rotation. Even if this is going down, it's still a positive rotation. So that brings me to one more thing that I need to add is that the theta calculated from B and theta calculated from A should agree, and I should also mention that C, the distance between the two mice, is the sum of RA and RB. It might be a little bit easier to see like this. But the distance from the center of mouse A to the center of mouse B is just RA plus RB. So if I pull up some formulas I made, this is just the stuff I already stated. The theta calculated from RB, oops, I didn't mean to click. The theta calculated from RB and the theta calculated from RA should be the same. That's all that's saying. And then, as we said earlier, theta A can be calculated by the negative of the YA distance divided by RA. And theta B is just the B arc length divided by RB. And we've already stated both these things. And then the last thing I mentioned before I pulled up this page was that the C distance is just RA plus RB. So that's all that this function formula is saying. What's nice about this picture here is that it's rotating about the center of mass. So it's really easy to find out what RA and RB should be. It's just half of C. But what if it's not rotating about the center of mass? What if it's rotating about some other point? What if it's rotating about this point or this point over here, and we have different lengths? RA and RB might not be the same. So we need a more general way to find it. But these relationships still hold true. So we need some way to relate directly from the YA, the vertical arc length displacement to the angular displacement. And both A and B should agree. Theta A is an unknown angle. Theta B is equal to A, but it's also unknown. YA is a known distance, and C is a known distance, and RA is unknown. So we have to somehow relate the known YA to the unknown theta A, because that's what we care about, is theta A. So we can use these formulas. We have enough formulas here to relate YA to theta A. or yb to theta b directly. I've color-coded the two halves of the equation, and this is just direct substitution. So theta a equals negative ya over ra. So theta a, we can swap that in directly for negative y over ra. And then the same thing with theta b. We could just directly substitute the equivalent of theta b. And then we can massage this a little bit. We can invert the entire thing, get ra on top, and then divide by ya would be on bottom, so we'd multiply. But ya would be on top on this side, and we would get this equation. This equation is, it's kind of useful to us, but it does not tell us how big. If we don't know RA, then we also don't know RB, and we're trying to get to theta A. So we need to go a bit further. We need to use C, which is a known distance. I've just restated in different colors what RA is. This is the same equation. I've just colored it differently. But if you remember from this equation, we can directly substitute RA. We can directly substitute this formula for RA directly into here. So I just took this and copied and pasted in this. Massaged it a little bit. You'll notice that there's an RB here and that there's an RB here. So we were able to take out, divide by RB. That gives us a 1 here, brings an RB to the outside. And we can massage this a little bit more, divide everything by this monstrosity. It comes on bottom here. And then we directly have RB. And I'm not going to go any farther, because once we have RB as a quote-unquote known distance using only knowns, like RB is completely defined by only knowns, then we have only knowns over only knowns, and that should give us our theta b. And we don't need to calculate theta a. You can maybe for redundancy or for to have a better measurement, but the math is very similar for that. So we have directly related a unknown theta b to only knowns yb and rb. And so this is the math to find out how much it has rotated, given just the distance between centers of mouse A and mouse B, and the lengths of YA and YB. So knowing rotation is good, but that doesn't tell us how much we moved. If we rotate about the center of mass, and there is no translation, and that's okay. But if we're rotating about something over here, then there will be translation. As you can tell, the center of mass, the green dot, actually moves as this thing rotates. So, so things to notice in this little animation. YB and YA are no longer equal, or at least equal and opposite. Now they're just not equal. The center of rotation is no longer at the center of mass. So now everything's rotating about this imaginary red point over here. RA and RB are no longer equal distances. And there's a new distance called D, and that's just the distance from the center of mass to the center of rotation. And so if we look at this, this animation here, we can tell that it's not just moving up, pause, it is not just moving up and to the side, but it's translating. It's not just rotating, but it's also translating by some amount y and some amount x. The y distance and the x distance, as you can tell, as this moves up, as theta increases, so does y, but of course it's not linear, because eventually as theta increases, it's going to wrap back round and come back to zero change. So after 360 degrees, it would have changed, zero amount. But the pattern for this is at 0 degrees, y changes by zero amount. At 90 degrees, so it would be up here, y would have changed by d amount. And when it goes off to the other side, 180 degrees, it would have changed by zero amount, because it wouldn't have moved up or down. it's the same total displacement. And then when it goes 270 degrees, when it's pointing down, it would have moved negative d distance. And then at 360 degrees, it would have gone back to zero displacement. And that is identical to the sine function. So it's safe to say that I haven't proved it, but it's safe to say that the delta y is just d times sine theta. And something I actually should have mentioned earlier, this d distance is just rb minus half of c. So half of c is the distance from b to c. So d is just rb minus half of c. You could also calculate it if you're wanting to use ya to calculate it. Then you could just do it is ra plus half of c. But I'm going to be using yb, so I'm just going to do rb minus half of c. The x displacement starts off at zero displacement, and then as time goes on, it'll get bigger and bigger and bigger, although technically more negative, but still a larger absolute value. At 90 degrees, we would have moved a distance of negative d, and then at 180 degrees, when it's pointing all the way to the left, there would have been negative 2d. And d is just a distance, not dimension. So d times 2 distance. And then at 270 degrees, it'll be pointing straight down, in which case there would be only 1 times d, negative 1 times d displacement. And then back at 360 degrees, there would have been no change. And it would be right here, which is right where we started. So 0 d. And that's that formula comes out to just d times cosine theta minus 1. So it's just cosine theta, but it's offset by 1. The entire graph's just shifted down. And that gives us all the information we need for a single step. So this is how to find the angular and translational displacements of a pair of computer mice.